in physics? Which chapters are you working on? Hello?
Hello, sir. Can you hear me now?
Yeah, yeah. Which chapters are you
Yes.
working on?
Like currently, we
Uh,
had magnetism in our test. So I was working on magnetism in matter and moving charges.
magnetism in matter. Current, electricity, capacitance and all is over.
Even
Capacitor
that,
chapter.
even that was there in the test, sir. Capacitance.
We have to do Gauss's law and capacitance, okay?
Yes, sir.
Let's focus on that in electricity. And what
Okay.
about your mechanics?
So mechanical friction, sir.
Friction chapter we had discussed, no? So questions and all are fine.
Yes, sir.
So if you have doubts in friction, you can ask me. Otherwise, we'll move on to circular motion and work per energy.
Yes, sir. Definitely.
Okay. Okay. So, Gauss's law, you have an idea what is happening?
Uh, yes, sir.
What is Gauss's law? Tell me. I want to quickly do the theory of these things so that you know what is happening. Okay. So, tell me what is Gauss's law?
So, so basically, the Gauss's law is about the net electric flux, which is coming. So it's coming out in the sense we have a Gaussian surface. We consider a Gaussian surface on a
Hmm.
plane,
Hmm.
and so the amount of net electric flux which is coming out through the plane in the
Correct.
direction of the area vector of that particular Gaussian surface.
Hmm.
Yeah, it's about that, sir.
So what is it? So law the law states what?
Um, it's like wait.
So there will be a statement also, no, of the law.
Yes, sir. It's like the phi is equal to q by epsilon naught is like the
Hmm. Okay.
equation.
What is this Q?
So q is the like the charge.
What which charge? Is it any charge or some special type of charge?
So that's the surface charge density.
It's not surface charge density. You have to create a closed surface. There's the charge inside that surface.
Hmm.
For flux. Okay, so in Gauss's law, there is some definitions. What is the definition of flux? Flux is equal to d phi. Small amount of flux is equal to E dot ds, right?
Yes, sir.
So what do you mean by E dot ds? So if there is a area vector like this, right? So if there's an area like this and field is horizontal E, right? Then area vector will be perpendicular to the area. S will be this area vector, right?
Yes, sir.
Now basically there is an angle theta. This is that angle theta, right? Theta is the angle between E and S, right?
Hmm.
So flux is defined to be E dot ds. That means E ds cos theta, right?
Yes, sir.
Basically, the amount of the field that crosses perpendicular to the area, right? So E cos theta would be field in this direction, no? E cos theta will be this component of this E. E sin theta would be this component, right?
Yes, sir.
So E cos theta into S is the flux through this surface. That means in the direction perpendicular to the area how much field is crossing that surface, right? So for example, if you have a or for field like surface like this, and area vector is straight up, right?
Okay.
And field is like this, then this angle matters. The flux will be E cos theta into S, right?
Yes, sir.
So this is the definition of flux. Flux through a surface is always defined to be this. Now, this is okay, but what is the use of this? The use of this is that Gauss's law law can be stated as flux through a closed surface. What is a closed surface? It is a shape, some shape, but it is closed, right?
Yes, sir.
Flux through a closed surface is equal to Q inside by E naught, right? So, because if there are some charges inside this, right? Q1, Q2, Q3, Q4, right? These charges will create some electric field through that surface, right?
Yes, sir.
Now, what the Gauss's law states that is that whatever is the electric field values could change also through the whole surface. So if you do the integral of E dot ds, right, over the whole surface, right,
Mm.
over the entire surface. So that means how much flux is coming out of the whole surface, right? That basically means that if you have a body, you take a tiny area here, and find the individual fluxes, right? D phi is equal to E dot ds1 here. D phi is equal to E dot ds2 here, right?
Yes, sir.
And when you do the integral, you are basically repeating it for all such areas, right? At each point of the surface, you are doing this d phi, right? And you are adding up all the fluxes, right?
Yes, sir.
With the understanding that flux coming out of the surface is positive and flux going into the surface is negative, right?
Yeah. Yes, sir.
Flux coming out is positive. Flux coming out is positive. Flux going in is negative. It's positive, right? Once you do this, you add up, you get the total flux through the surface is equal to total flux coming out of the surface, right? Correct.
Yes, sir.
That is equal to, that will always be equal to the total charge inside, summation of charge inside by E naught. That will always be equal to the summation of the charge inside by E naught. You understand?
Yes, sir.
So, so it doesn't depend on what are the charges outside the system. It doesn't depend on Q5. It depends on Q1 plus Q2 plus Q3 plus Q4. Okay.
Okay, sir.
Because the logic of this is clear that if there is a charge outside Q5 and there is a surface like this, right? This will create a field, but whatever field line comes will exit also, right?
Yes, sir.
This will create a field and will cause some flux, but flux coming in will be equal to flux going out. You understand?
Yes,
So
sir.
this doesn't influence the total flux out of this body, right? Does not affect, doesn't affect the total flux through the body. Correct?
Yes, sir.
So now that we know Gauss's law, the definition, Gauss's law definition says total flux out of this body will depend only on the charges inside that body, right?
Yes, sir.
Once we know the definition, now we need to know some applications. So for example, how will we use Gauss's law to do what? Tell me.
So basically, Gauss's law applications are there in the
Hmm. What is the purpose of doing this Gauss's law? There must be some purpose, otherwise why would we learn it, right?
Um,
Think about it. Where do we use this Gauss's law? How do we use it? We use Gauss's law to find electric field, no? Hmm?
yes, sir.
So, basically what happens is, suppose there is a spherical surface and there is Q1 here and Q2 here. We will be able to say that total flux outside coming out of this is going to be Q1 plus Q2 by E naught, right? Total flux of the electric field will be
Right.
equal to, flux will be E dot ds integral will be Q1 plus Q2 by E naught, right? Correct.
Yes,
But
sir.
in this case, we'll not be able to find the E dot ds. Can you tell me why? Suppose Q1 was at the center and Q2 was off center. We'll not be able to find E from here. Q2 was off center, right? This was the case that I'm thinking about. If it was just one charge at the center, right, I would have been able to find E. E would have been Q1 by 4 pi r square E naught. How did I do that? I did E into 4 pi r square is equal to Q1 by E naught, right?
Yes, sir.
I did this and then I wrote the E value. Correct.
Yes, sir.
But I cannot do the same here. I can only write till here. I cannot write what is E. Why
Hmm.
is that? Here you have to understand some limitations of this Gauss's law. Okay, so Gauss's law states that E dot ds is equal to Q in by E naught. But here, if the charges are Q1 and Q2 like this, Q1 is at the center and Q2 is not at the center, right? So when you do E dot ds, field here is different from field here, no? And field here is different, right?
Right, sir.
You understand this Q2 is ruining all the symmetry of the question, right? Q1 is at the center, but Q2 is not at the center, no? So that will change the amount of field from these points, right?
Hmm. Yes.
Because it changes the amount of field at these points, uh, you cannot really evaluate the integral, no? Because E is changing, right? The problem is that if E was constant throughout, right? Correct. If,
Okay.
if E was constant throughout the surface, right? What I would have done is E is constant over the surface, so E comes out of the integral, right?
Yes, sir.
If E was constant over the whole surface, E would have come out of the integral, and integral would have been a simple area of the surface, which is 4 pi r square, right?
Hmm.
Is equal to Q in by E naught, right?
Yes, sir.
Then I would have gotten the answer. But here, is E constant over the whole surface? No.
No, sir.
So because E is not constant, now you cannot take it outside the integral. So then you are stuck with this value. You are stuck here only. You cannot go further than this, right?
Yes, sir.
So then you know that flux outside will be equal to Q1 plus Q2 by E naught, but you cannot decide what is the field at each point. You can only say what is the flux. Gauss's law is still valid, but it doesn't help us to find field, right?
Right, sir. Understood.
So the limitations of Gauss's law are a few, like limitations. What are the limitations? One, first of all, integral E dot ds is equal to Q inside by E naught. First of all, field E must be uniform over the surface that you have chosen. must be uniform or constant over the Gaussian surface, right?
Yes, sir.
If it is not constant over the Gaussian surface, then you cannot take it outside the integral, right? If it is constant, you can take this outside. And then it becomes a question like this: E integral ds, right, is equal to q in by E naught, right?
Yes, sir.
That is good because then you can find this out, right? Second thing, the area of the surface chosen of the Gaussian surface should be easy to find. You understand?
Mm,
See, this integral is also having, it has to be easy to find, na? Otherwise what is the point?
okay, yes, sir.
Agar if I take a Gaussian surface like this, even if I know that E is uniform, right?
Hmm.
How will find the area of the surface? You
Right.
understand the problem?
Yes, sir. Understood.
Even if I take it outside, how would I find the area of the surface? I don't know some formula for area, no? It will be a hard integral, right?
Yes, sir.
So, so two things have to happen. First of all, E must be constant over the Gaussian surface. So you have to choose your Gaussian surface in such a way that E remains constant, right?
Yes, sir.
So one basic thing to ensure then that E remains constant over the surface is that your charges inside should be placed in a symmetrical manner with respect to the surface, right? It will not
Right,
work
sir.
if you have chosen a spherical surface and charges are arbitrarily placed, right?
Hmm.
And clearly this point will be different field than this point, no?
Right, sir.
You understand? So whatever
Yes.
is the charge distribution, you have to choose a surface which is symmetrical with respect to that charge distribution, right? You should not be able to say that one point of your surface is better placed as opposed to some other point, right?
Right, sir.
So that is a key criteria. Otherwise, E will only not be constant. Then you cannot do anything. You will be stuck here only, right?
Yes, sir.
And after that, the second step is making sure that the surface that you have chosen, you can find the area of the surface, right? You should choose nice and symmetrical figures so that you can find that area, correct?
Yes, sir.
So these are one or two things that are super important. So now that you know all this, tell me, there is a plain sheet of charge, plain sheet of charge, zero thickness. Okay, when you say plain sheet of charge, you mean zero thickness, zero thickness. 1 second, hold on for a moment.
Yes, sir.
So if there is a zero thickness plain sheet of charge of surface charge density sigma, sigma is the surface charge density, then
Yes,
what
sir.
is the field at this point? And if there is a conductor, right,
Hmm.
of some thickness, right?
Yes, sir.
In that case, also surface charge density is that only sigma. Sigma is the charge density. It's a conductor. Then what is the field at this point? And what is the difference in the field and all, and why is that happening? Basically, in both cases, if you don't want to talk about this, in both cases, say Q charge was there. Q charge, and here also Q charge is placed on this sheet and this conductor, right? And A area. A is the area, right?
Okay.
So tell me, what are the fields in both the cases by applying Gauss's law? Do that calculation.
Yes, sir. Sir, in the first case,
Hmm.
should E be like Q by E epsilon naught A?
No, slightly wrong. Think about it properly, draw a Gaussian surface and then say.
Okay, sir.
In the first case, when you draw a Gaussian surface, which type of Gaussian surface will you draw?
Sir, I drew a cylinder, sir.
A cylinder that crosses on both sides, right?
Uh,
You cannot draw a cylinder only on one side, right?
oh, yes, sir.
If you draw a cylinder on one side, what is the problem? Just a cylinder that touches the surface and comes on this side, right?
Hmm.
There is a problem. Tell me what the problem is with that. I mean, you can draw whatever type of surface you
Surface,
want, right?
right? It's not going to be the charge inside the.
No, let it touch, let there be a tiny charge inside, and
Okay.
then if on one surface the charge is there, no? On just touching that surface, right?
Hmm.
Why is that cylinder not going to work? That cylinder is not going to help you at all. You understand what I'm saying, no? Which type of cylinder?
Yes, sir.
So
The one
suppose
with
I
the
had drawn
charges.
a cylinder like this, right?
Yes, sir.
And here there is charge, right?
Huh.
Why is this cylinder useless? That cylinder is going to be useless for your calculation. But on the other hand, if I draw a cylinder crossing it, right? Like this, one side this much and one side this much, right?
So because there is no symmetric nature in the charge, right?
Symmetric nature in what?
The charge distribution, sir.
Explain further, tell me why.
Sir, okay, how do I explain? So in this case, like the one in which it is only on one side,
Hmm.
right? So there is no symmetric nature of the charge because, uh,
Uh-huh.
well, it's on one side and
Charge is on one side. So,
right.
so can you say that field at all points on your cylinder is same?
No, sir.
You can obviously not say that, no? Because one side it is on the surface and other side is so far, right?
Yes, sir.
But on that other case, right? You can say that uh, you have still some doubts, but at least you can say field here will be same as field here, right? Right?
Yes, sir.
But what about the curved surface, right? You cannot say with guarantee that field at every point is going to be same. on the curved surface?
No, sir.
Actually, you can, because field on the curved surface will be zero under some conditions. On the entire curved surface, field is zero if the sheet is large.
Mm.
Can you think about why? If the field is large, the curved surface field is going to be zero. If the sheet is large, field here is zero. Here is zero. Everywhere. Why is that so? Because if the sheet is large, sorry, if the sheet is large, what happens is that the
Sir,
component
the
of the
huh.
becomes zero, whichever is parallel to that surface, right?
Yes, sir.
Because it looks like there is another area, surface charge density above and below, right? They cancel each other off. Like if my this surface is very large compared to this distance, right? This point, right? Then there will be a corresponding charge here that creates a field like this, and a corresponding charge here that creates a field like this, right?
Yes, sir.
So the net component in this direction will be zero, right? So
Ah,
all the field will be in this direction only, right?
okay.
Because there will be an upward portion also, and there is an equivalent downward portion also.
Yes, sir.
So that only happens if the surface is large compared to the distance that you are taking it at, right?
Sir, can we also talk about like I understood what you said, sir, but can we also talk like that the n vector, like the normal vector which comes out of the surface, sir, it will be like perpendicular to the E. So,
No, that is what we are understanding. Why will it be perpendicular to you?
oh,
Because E has no component in that direction.
okay, okay, fine, fine, fine.
That is what we are saying. That E has no component in that direction only because the the plane sheet of charge is large as compared to the distance at which you are measuring the E, right?
Yes, sir.
Then it looks from that point it looks as if the sheet extends in all directions infinitely, very far distance, right?
Yes, sir.
Basically, think of a 1 meter square area sheet, right?
Huh?
And a point that is 1 millimeter away from the sheet, right?
Okay.
So the area is much bigger than this distance, no?
Yes, sir.
So at 1 millimeter above the surface, it will look like the sheet is extending in all directions, right? Forever.
Right. Yes, sir.
So every point on that sheet, no matter where it is, you'll find a corresponding point on the opposite side,
Oh, understood. Okay.
right? And you'll be able to cancel that, right? You'll be able to cancel the fields like that. So only field component that will be left is perpendicular.
Okay. Okay.
So now in this case, what will come as the total flux? Flux will be due to the two outer surfaces, right, of the cylinder, E into S plus E into S, right?
Yes, sir.
E into S into E into S plus E into S is equal to Q inside by E naught, right, for your cylinder.
Hmm.
So let's say S is this area, S is this area. So 2ES, because field here is same as field here. So it is ES plus ES, right?
Yes, sir.
Is equal to Q inside by E naught. What is Q inside? Q inside is S into sigma, right? Sigma is Q by A, right? Correct.
Yes, sir.
Q by A S E naught, and S cancels and field becomes Q by 2A E naught, right? So that can be written as sigma by 2 E naught, right?
Right, sir.
Correct.
Yes, sir.
Okay. Now, so due to a plane sheet of charge, right? The field is sigma by 2 E naught, right?
Yes, sir.
Now, on the other hand, due to a conductor, it is going to be different. It is going to be sigma by E naught. Okay. So if your conductor has surface charge density sigma on this surface, right?
Yes, sir.
Then you can find the flux in a similar way, but this time you should take a cylinder which goes till inside the conductor and comes out.
Sir, in this, like, I just have one question
Hmm.
which I want to ask. Like, when we consider a cylinder as a
Hmm.
Gaussian surface, sir,
Hmm.
sir, are we also talking about the surface charge density on that particular flat surface, or it is just inside the conductor what we're talking about?
No, it is in all the charge inside the cylinder you care about.
Oh, okay.
Yeah, sorry. Tell me.
Uh, Understood, sir. Like what you said.
All the charge inside the cylinder is what is important.
Okay.
So it could be on the cylinder also, but it has to be inside or on the cylinder. So here you can take one cylinder which ends inside this, right? Ends inside this, and one half that goes outside, right?
Okay.
So field inside a conductor is zero. So field is here zero, right?
Right, sir.
And field here will be something, same logic, E into S. So you'll do ES is equal to Q inside by E naught. And charge inside will be the charge trapped here, right? So that will be sigma S by E naught. So E will be sigma by E naught in this case, right?
Yes, sir.
Now, what happens is, why is it sigma by E naught? Because field is zero inside the conductor, right?
Right, sir.
Understand? Now, a conductor can be thought of as basically two plane sheets.
Okay.
Charge also always resides on the surface of a conductor. Okay, charge always resides on the surface of the conductor. Why is there no charge in the interior? Why is there no charge in the interior?
Sir, because the free electrons which are there,
Hmm.
they are in the metal lattice or the conductor lattice. They are
Uh-huh.
always basically jumping in the orbitals on the surface.
No, so the reason is because there is zero electric field inside the conductor. If there is, because if there would have been an electric field right inside, then the electrons would have moved in the opposite direction, right? Correct.
Yes, sir.
If there is an electric field E, non-zero, then electrons would have moved because they are free electrons, right?
Yes,
They would have moved in such a way that would have neutralized the field, right?
right, sir.
So because of which what happens is, there is field is zero inside the conductor. Now, if field is zero inside the conductor, you can take any Gaussian surface, right? Inside, right?
Yes, sir. Yes, sir.
And field is zero here, here zero, everywhere zero. So flux through the Gaussian surface must be zero, right?
Yes, sir.
Therefore, Q inside that Gaussian surface must be zero. If Q
Okay.
inside that Gaussian surface is zero, that means there is no net charge inside the conductor, right?
Okay. Yes, sir.
So basically, if you have a metal ball, right? Metal ball, suppose, right? Now, because of the properties of the conductor, electric field inside a conductor is zero. That you have to understand why. Why is because if there was a non-zero electric field, electrons would move, right? They are free to move,
Yes.
correct? And if they move, they will neutralize that field, right? So
Right.
then you can take any size spherical Gaussian surface inside. Field is zero everywhere, right? So flux is zero. So there is no charge. Q is zero inside, right? Correct.
Yes, sir.
So you can take a very big, also very big Gaussian surface, which is just less than the total surface, right? So field is going to be zero inside that also. So flux is zero. So Q is also zero inside, right? So if you give a charge on the metal, all of it will be on the surface, right? That
Hmm.
is the property of a conductor, correct?
Right, sir.
So here also all of it will be on the surface. So now you can think of it as this whole metal conductor can be thought of as two plane sheets. Okay, correct?
Right, sir.
There's sheet 1 and sheet 2, right? Correct.
Yes, sir.
If you had given a charge Q on the metal, then Q by 2 would have come here and Q by 2 would have come here, right?
Right, sir.
Correct. And or instead of working with Q by 2, you can just say sigma is the charge density here and sigma is the charge density here. There is no difference between these two surfaces, right? So then this plane sheet would have created sigma by 2 E naught here and sigma by 2 E naught here, every direction, right?
Yes, sir.
From the previous derivation. And this plane sheet would have also created sigma by 2 E naught here, right? And sigma by 2 E naught here, right?
Yes, sir.
So notice that the field outside here is addition of these two sigma by 2 E naughts. So that becomes sigma by E naught, right?
Oh, yes, sir.
And field inside becomes zero because these two cancel, right?
Right, sir.
And field here is also sigma by 2 E naught plus sigma by 2. That becomes sigma by E naught,
Oh, okay.
right?
Yes, sir.
So field inside and outside a metal conductor, you know how to get, right? It is sigma by E naught because it is the sum of two charged plane sheets of charge, right?
Right.
Okay. Uh, Now there are many other examples and all, but we'll do just one example which is in the exercise last question of HCV. Uh, so question is like this. Suppose we label these surfaces. These are all conductors.
Okay.
And I have given a charge minus Q on this and charge 2Q on this, right? I have given these charges on this conductor.
Okay.
The three metal bodies. Now you have to find final charge distribution on each of the surfaces. Final charges on A, B, C, D, E, F. So Gauss's law you should use to find that. This is the last question or second last question of HCV Gauss's law exercise. Okay. So you need to understand this. Once you understand this, other questions should be okay. You have to just apply the Gauss's law.
minus Q. Okay. Uh,
Mm-hmm.
it's Q Q not.
What are you thinking, Tilman?
Sure. Sir, by the I don't know if it is right, but by the last discussion we had on the the like you said, right, the conductor is basically two plates.
Mm,
So in this case, I would consider like the CD thing
mm,
between the two plates AB and EF.
mm-hmm,
So in that case, basically, if we calculate the electric field,
mm.
uh, wait, I'll just tell you the value. It's 2Q and is Q 2Q by W. That is 2Q and then minus Q. That's Q by epsilon naught. And so according to that, we should have
Mm.
an electric field of Q by 2E naught in the like on the CD plate.
We have to find charges on each of the surfaces, right?
Right, sir.
And from there, you will be able to only find field here and so on. Suppose you have 4 points, 1, 2, 3, 4. You need to find, say, charges. Once you find on A, B, C, D, E, F, you'll be able to find E1, E2, E3, E4, right?
Yes, sir.
Before you find the charges, you cannot find E1, E2, right? Only if you know charge on this plate, then we will be able to use that metal sheet of charge, right? Correct?
Right, sir.
So in this question, think of applying Gauss's law. Okay. So I don't know what is the charge on this. So let's take a variable Q, right? On this surface, right?
Yes, sir.
So what is the charge on this surface then? Remaining charge, right?
Okay.
Correct.
Yes, sir.
So if this is the charge on this surface, let's do Gaussian surface like this. From here to here, right?
Okay.
So field here is zero inside the conductor. Field here is zero inside the conductor, right? So flux through this whole Gaussian surface is zero, right?
Yes, sir.
So then charge inside must be zero. So if this is 2q minus q, this must be q minus 2q.
Okay.
Because charge inside has to add up to zero, right?
Yes, sir.
So if this is q minus 2q, there is zero total charge on this, right? So this must be 2q minus q, because the total charge on this middle one was zero, right?
Right, sir.
So this is 2q minus q. Now same logic, this becomes q minus 2q. Again, you can take a spherical, take a cylindrical surface like this, right? Q minus 2q comes here also, no? Because field inside is zero, no? Field inside is zero, so flux is zero, right?
Yes, sir.
So once this surface is q minus 2q, this surface has to be something that adds up to total charge of minus q, right? So minus q minus small q plus 2q. So it becomes q minus q, right? Here.
Right, sir.
So
Two.
these are the variables. Charges are coming q, 2q minus q, q minus 2q, 2q minus q, q minus 2q, and q minus q, right? These are the individual charges that are appearing, right?
Right, sir.
So now you still have not found your small q, right? That is the main thing. If you can find your small q, then it is over, right? This small q was a variable that is still unknown, right? This one.
Right, sir.
So how do you find that? Now to find that, you have to take a big Gaussian surface. So take a, okay, so I want to draw it in a different figure. Wait 1 second. Uh, Suppose you have one conductor like this here, total 2q, another conductor like this here, 0, another conductor like this here, minus q, right? Now, our problem is that this is unknown q and this came as capital Q minus q, right? What did it come?
So it came as capital Q minus small q.
Correct. This is what it came. Now, I have to find the charge on this and this. So what happens if I take a Gaussian surface like this and this is very far away?
You mean to say like the from the point Q to Q minus Q and everything inside it?
No,
Oh no.
no.
Okay.
I'm taking it outside very far away.
Okay.
This is my Gaussian surface and this is my Gaussian surface. Again, very far off,
Okay.
right?
Hmm.
If I do this, Then here field will be something, right? Correct. Here field will be 0, right?
Yes, sir.
And similarly here field is 0 and here field is something, right?
Hmm.
If your points are very far away, these two Gaussian surfaces are at a very distant point, then this side and this side, will you see any difference?
I
That is the whole point of taking it at a very distant point. Suppose the plates had separation of 1 millimeter or 1 millimeter, whatever, the separation between the plates, right? And this was 100 meters away. What is the difference between here and here? No difference, no.
no difference, sir.
If you look at 1 kilometer away from both the sides, then it will look like some charge is there, no?
Yes, sir.
It doesn't matter whether you look from here or look from here, right?
Yes, sir.
So here field is E, and here also field is E if you're looking very far off, right? Correct.
Yes, sir.
In any direction, the thing that happens is that from far off, it looks like a same one plate of some charge, right? You cannot
Right, sir.
notice that it is actually three separate plates, right? From
Right,
far
sir.
off, it looks like one plate of some charge. That's why it looks same field, correct?
Okay, sir.
So once you get that, then you can do Gaussian surface E into S is equal to Q inside by E naught, right? For this one. And same E into S is also equal to Q inside by E naught for that one, right?
Oh, right. Yes, sir.
So then you will get an equation saying Q inside here is small q by E naught is equal to capital Q minus Q by E naught,
Yes.
right? Because
Yes.
it's equal to the same E into S, right? So you will get an
Right.
equation saying Q is equal to capital Q minus Q, correct?
Yes, sir.
And that will give you the value of small q. Small q will become Q by 2, right? 2Q is equal to Q, so Q is equal to Q by 2, right? So
Right,
this
sir.
becomes Q by 2, so this becomes 3Q by 2 minus 3Q by 2, 3Q by 2 minus 3Q by 2, and this becomes Q minus Q by 2, so Q by 2, right? You understand?
Yes, sir.
So you get all the charges now. This is because the outer surface, the outermost surface, you were able to say that those charges will be equal, right? Q will be equal to Q minus Q,
Yes, sir.
correct? And because of which, what happened is you got the value of small q, right? So now the question becomes very easy now. Now all the charges at each surface you know, right? Correct?
Right, sir.
All the charges at each surface, if you know, then you can, at any point, you can find the field. Suppose I knew that this was q by 2 and this was 3q by 2 and this was minus 3q by 2 and this was 3q by 2 and this was minus 3q by 2 and this was q by 2, right? Correct.
Yes,
Then
sir.
find the field at this point. How will you find field here? Which is not a far off point, it's a nearby point here. Let's label it A, B, C, D, E, F, right? Have you understood how we got the whole charge distribution?
Yes, sir.
We took a far off point and that gave us the idea that from a far distance, both sides, it will look the same, right?
Yes, sir.
And because it looks the same, then the charge on the outer surface of both the sides will be same, right? The outermost surface from both sides will have equal charge, right? Correct. So now, what is the field here? Field here. This is not far off point. This is nearby point. Okay. That will be due to field due to A, right? Due to A and due to B and due to C and due to D and due to E and due to F,
Right, sir.
right?
Yes,
It
sir.
will be because of each plane sheet of charge. Each plane sheet of charge. This is a plane sheet of charge. This is also a plane sheet, right?
Right, sir.
They are all at close by distances from this point, so they will create their own individual fields, right?
Yes, sir.
So which fields will cancel? Field due to a plane sheet of charge, I know formula is sigma by 2 E naught, right? So it depends on the sigma value, right? So this field and this field will cancel. This field and this field will cancel, right? Correct?
Yes,
So they are in opposite direction. What will happen is the added field of this and this will come, right? Correct. So 2 times sigma by E naught, where sigma is due to this charge density,
E and F, right?
A and F,
Okay.
right?
Yes, sir.
So it becomes sigma by E naught, where sigma is Q by 2 E naught A. This is the field, right?
Yes, sir.
Because charge was Q by 2 and area was A, right? Similarly, if you want to find field here, field at a point E2, and second point is somewhere here, right? E2.
Yes, sir.
Now this will be due to all the plane charges, but the directions will be different. Field due to A will be this side, field due to B will be this side, due to C will be this side, due to D will be this side, due to E will be this side, and due to F will be this side, right?
Yes, sir.
Now you can find out what it is by doing sigma by 2 E naught due to each, right?
Hmm.
So be careful, some of the fields may cancel and all, right? Correct?
Yes, sir.
So q by 2, 3q by 2 in this side, and then minus 3q by 2 it adds, right? And then 3q by 2 in this side. So this cancels this one cancels this one, right? And minus 3q by 2 is again this side, and q by 2 is this side. So this one cancels this one, right?
Right, sir.
So net field is due to this surface, which is this side, and this surface, which is also this side, right?
Hmm.
You understood?
Yes, sir.
So similarly, you can find field at all points, right?
Yes, sir.
So in case this was the case for 3 bodies, right? Suppose I have 2 of them and I give 0 charge on this and q charge on this. Now there is a shortcut way to find all the charge distributions and every field and all.
Okay.
I mean, not field, there's a shortcut to find the charge distribution.
Ah.
Now, what you should remember is that if 2 conductors are placed near each other, right? The
Okay.
charge on the outermost surface and this surface will be equal, right?
Only when they are placed close together, right?
2 conductors are placed nearby each other, and when they are influencing each other, right? If they are placed far apart anyway, it doesn't matter.
Yes, sir.
If they are placed far apart, then what? Then I can easily say that this q will divide q by 2, q by 2, that's it, and this will be uncharged, right?
Yes, sir.
So that is not the case we are worried about. We are worried about when they are placed close to each other, what is the charge distribution, right? Correct?
Yes, sir.
So this will be, we know from the previous discussion that outer surface charges are equal, no? You remember, just like we did that Gauss's law thing.
Yes, sir.
So outer surface charges are equal, and the charge will be equal to the sum of the total charge on the entire system by 2. So in this case, it is 0 plus q by 2. It is going to be q by 2. Here it will be q by 2. Here it will be q by 2. So here it has to be minus q by 2. Here it has to be plus q by 2. See, it adds up to q.
Yes, sir.
You understand how it is fitting now, right?
Right, sir.
So the outermost surface charge, right? This surface and this surface will have always equal charge, and that will be equal to the total charge on the whole system by 2. Okay.
Right, sir.
If I had put minus 3q and plus q, right, on these two, right, the outer surface here and
Okay.
here will have charges of minus q and minus q. Why? Because sum of the total charge is minus 4q, right, or minus 2q, right,
Yes, sir.
divided by 2. So now how will it happen? Minus q here, then minus 2q here, and then 2q here, and 2q minus q is q.
Yes, sir.
Correct?
Yes, sir.
Any two pair of interior opposite surface have equal and opposite charges, right?
Yes, sir.
So in case it was a question like this, I give q here, minus 2q here, and 3q here, right? This surface and this surface will have total charges of q and q,
Okay.
right?
Yes, sir.
This will have q here, so 0. Huh? That is weird.
Minus 2q and 2q. 2q, 3q minus 2q.
It
0.
is fitting, but I'm feeling a little doubtful about this. Maybe
Yes.
it is possible. I've not seen such a case usually. That doesn't seem very possible. Okay, but this minus 2q is attracted to this plus 2q. No? You understand?
Yes, sir.
This and this are being close together, so no charge here, so no charge here, and q here, and q here. Makes sense. You understand?
Yes, sir.
The key logic, though, the key logic by which it is, because of which it is working, is because if you look at it from far off, right? If you look at it from far off, the whole system looks like one plate, one pair of plates, right? This side
Yes.
and this side, and has a total charge of what? 4q minus 2q, 2q, right? If you look from 1 kilometer away, no, it looks like one plate of charge 2q, right? So
Yes.
therefore, q on this side and q on this side, right?
Yes, sir.
Here it looks like a one big plate of charge minus 2q. So minus q on this side and minus q on this side. Correct?
Right, sir.
The whole logic because of which this is happening. But
So
actually, you're doing it like Gauss's law.
one small doubt I had in the so when you explained those three plates
Mm,
and you told about taking the Gaussian surface at a very long distance,
mm,
right, sir? So at the point in the conductor which is inside the Gaussian surface, the electric field will be zero, right?
mm.
So then, sir, I didn't understand at the extreme point how is there some electric field available?
Because there is some charge, no?
Uh, okay.
Some electric field available because that question we had given 2q and minus q, right?
Yes, sir.
This is a net charge, right?
Yes, sir.
Will not create, that will definitely create some electric field, no?
Yes, sir.
Also, on this surface, if there is charge and you have taken this Gaussian surface, then there is q inside, no?
Right, sir.
So flux will be there, but flux cannot be here because field is zero here.
Okay, 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 sir.
So flux has to be on this one, no?
Yes, sir. Understood.
We have just included that outer surface, right? So there is charge inside this Gaussian surface, right?
Yes, sir.
The whole point is that this flux Es is same as this flux, right? This one here. That is the whole logic. This Es and this Es are same because you are going equally far on that side also. It's very far, right? It looks like one big plate from far off. It looks like one plate of total charge Q, 2Q minus Q, right?
Yes, sir.
So that one plate will have Q by 2 here and Q by 2 here. Q by 2 here and Q by 2 here from both sides. And that is what we got also. Q by 2 here and Q by 2 here. Q by 2 here, then 3Q by 2 minus 3Q by 2, 3Q by 2 minus 3Q by 2, and Q by 2, right?
Right, sir.
Okay, so this is Gauss's law. Now there are multiple types of questions you should practice from the HCV book. HCV book has some 30 questions. If you do all those 30, then there will be all questions you can answer of this chapter. Okay, so try these questions, Gauss's law questions. Okay.
Yes, sir.
Similarly, we had discussed a little bit of capacitors. I don't know how much theory was left. What are the parts of capacitor theory that you don't know?
Sir, don't know in the sense like when I was reading, I asked you one question, right?
Uh-huh.
Uh, just a minute. So in that it was like in the parallel plate capacitors, in they were mentioning like in linear dielectrics and stuff,
Uh,
uh, sigma minus sigma p is should be proportional to sigma divided by k. So I didn't understand that.
okay, so basically dielectrics part you have to understand. First of all, dielectrics, why they happen, right? What are dielectrics?
Uh,
Dielectrics is
they are
basically
something
any
with
insulator,
hmm,
right? Any insulator is known as a dielectric. Examples of dielectric are air, glass, water, whatever, right?
yes, sir.
These are all non-conductors. So basically dielectric is any non-conductor, right? So now what happens when you put a non-conductor between the plates of the capacitor, right? The plates of the capacitor create an electric field E, right? Correct?
Yes, sir.
Now this E field will try to actually push charges in this direction, right? Positive charges in this direction and negative charges in this direction.
Yes, sir.
Correct?
Yes, sir.
Now, in a dielectric, what happens is there are molecules, and molecules sometimes have some dipole moments inside, right? So, molecules have some charge distribution which is not equal, right? Sometimes there are polar molecules. For example, water is polar, right? In the sense that oxygen has slightly negative charge and hydrogen has slight positive charge, right?
Yes, sir.
So because of that polarity, what happens is uh, they arrange themselves in such a way that the negative side will point towards the this field, no, this place, right? The molecules will arrange themselves in such a way that the negative will point towards the positive plate of the capacitor, right?
Yes, sir.
And the positive end will point in this direction, right?
Yes, sir.
Because of which there is a net dipole moment, right? Like this, right? Negative is this side and positive is this side, right?
Yes.
So there is
Okay.
a dipole moment like this, no?
Huh.
So because of a capacitor's electric field, there is a net dipole moment like this, right?
Okay.
So what it feels like is that this dipole moment is basically a field in the opposite direction, no? Plus to minus, right? Right?
Yes, sir.
The original field was E, this is E dash in the opposite direction, right?
Okay.
So, so the net field that you see inside the thing is lesser than the original E minus E dash.
Okay, because of the dipole. Huh.
Because of the dipoles, there is a dipole moment per unit volume, which is called polarization. You should read about all of this in the book. Polarization is called the dipole moment per unit volume.
Yes, sir.
Per unit volume. So the material gets polarized, and there is a lot of dipoles in every unit volume, right?
Okay.
Because of which, what happens is that the E field that would have happened if it was in vacuum, right? That is reduced now, right?
Okay.
And E field is reduced, and how much does it become? It becomes E by K. Okay. Upon reduction, upon introducing a dielectric, the net field becomes E by K. Okay. So the presence of a dielectric, the presence of a dielectric like this, right, causes two things. It causes capacitance of the system to become K times C and field inside to become E by K. Okay. These
Yes, sir.
are the two things that you need to keep in mind. Capacitance of the system becomes K times C and field becomes E by K, right? So what you can say is that there is charge induced, right? There is field is created because of charge, right? So if sigma by E naught was the original field, right? Right?
Okay.
In vacuum, then sigma was equal to E naught into E, right? That was the charge density on the plates, right?
Yes, sir.
But now new field has become E by K. So you can say that effectively sigma is what? Sigma by E naught effective is E naught E by K is my effective sigma, right? Right? Correct.
Yes, sir.
So basically some of the charge has been slightly neutralized, right? Because of the opposite charge that has come on this, right? And this plus Q has been slightly reduced because of this, right? You're dealing with an effective charge which is Q minus some Q induced, right?
Yes, sir.
Q minus Q induced will be the Q effective, right?
Yes, yes. Hmm.
So so you get Q induced is equal to Q minus Q effective, right? Which is
Hmm.
equal to sigma induced now. Sigma induced will be equal to sigma minus sigma effective, right? Which is equal to sigma was E naught E minus E naught E by K, right? So it
Okay.
becomes E naught E 1 minus 1 by K. E naught E was sigma original, right? Sigma into 1 minus 1 by K is my induced sigma, right?
Yes, sir.
So, so sigma induced means the induced charges is equal to sigma into 1 minus 1 by K, right?
Yes,
And
sir.
that means that basically only 1 minus 1 by K portion will be left, right? Effectively. Like, like no, when you subtract this, you get sigma by K, right? Sigma effective is equal to sigma minus sigma induced, which is equal to sigma minus sigma 1 minus 1 by K, right? So that becomes sigma by K, no?
Yes, sir.
So effective charge is sigma by K, right? So that is what happens when you introduce a dielectric. Dielectric, this K value is a dielectric constant, okay? K value is dielectric constant. So now what has happened is field has reduced, capacitance has increased, all the other formulas are the same as it is.
Okay.
Q is equal to CV and all, right?
Yes, sir.
So potential, if you have still connected it to the same potential and all, then charge has to, more charge can be stored now, right? Because capacitance has increased, right?
Yes, sir.
If the voltage is same and you have increased the capacitance by K times, you can store more charge, right?
Right, sir.
Correct. You can also understand this in terms of you can say that E naught was the permittivity of free space, right?
Huh?
Permittivity of free space. This was a constant, right?
Oh, yeah, yeah.
Now, if you are not in free space, not in vacuum, then E will take the place of E naught in everything, right? And E will be K times E naught. Okay.
Yes, sir.
So if you want to say what is the electric field due to a point charge? Electric field due to a point charge in space. But the space is filled with a dielectric of constant. Dielectric constant is K, right? So there is a Q charge and this is lying in space, like say air, right? Air's dielectric constant is close to 1, but if it was not close to 1, it was K. The electric field at this point will not be Q by 4 pi naught E naught R square, right? Because this E naught was referring to vacuum,
Yes, sir.
right? In this case, it is in a dielectric, right? Electric field will be Q by 4 pi E
Epsilon not, sorry, epsilon
R
into
square.
K. Yeah.
This is E, right? Which is equal to K into Q E naught.
Huh. Okay.
Basically, what has changed? E naught has become K E naught.
Huh.
Is the
Yes, sir.
It is the permittivity in the dielectric, not in free space.
Okay. Okay. Okay.
In dielectric, right? And this was free space, correct?
Okay.
So basically what happens is that field becomes 1 by K times of its original value, because of which capacitance has to increase. Okay. Capacitance has to increase because field has become 1 by K times. So potential difference has become 1 by K times. And if it was an isolated capacitor, right? Suppose there was an isolated capacitor. This is vacuum. This is initial situation, right?
Yes, sir.
Initial, right? And there was charge Q and minus Q. And final is this. You have inserted a glass slab inside, right?
Okay, sir.
Correct.
Yes, sir.
So Q and minus Q remain same, no? Q and minus Q is same,
Yes,
right?
sir. Yes, sir.
It is isolated, so charge cannot escape anywhere, right? So Q is equal to CV has equation has to still be somehow valid, right? But what has happened is V has changed, right? V has changed drastically. Potential difference generally is equal to E into D, right? But now it is ED by K, right? Correct.
Yes, sir.
Because of the glass slab, it has become ED by K. So
Yes,
what
sir.
should happen to the C? It should become KC. Then only Q will be equal to CV, no?
Yes, sir. It will continue.
Correct. So for an isolated capacitor, you can see easily. It is easy to understand why field must become E by K, right? That is intuitive to understand, right?
Yes, sir.
Field becomes E by K because polarization and dipole moments oppose the total field, right? Correct.
Right, sir. Understood.
Once that field has reduced, and if there was no other charges could flow and all in the system, then now it is obvious why capacitance must become Kc, because charge was fixed and potential has reduced. So what has to increase? Capacitance.
Capacitance. Yeah.
So C becomes Kc, right? So after that, everything else you keep doing the same formulas and all, whatever you've learned, energy Q square by 2C and so on,
Yes, sir.
right?
Yes, sir.
So
Yes, sir.
initial energy was Q square by 2C. Final energy here, Q is same. So Q square by 2Kc, right?
Oh, okay.
Right? Here Q is same, no? Q is constant,
Ah,
isolated, right?
yes,
In
sir.
some questions, the battery was connected. So potential difference would have been constant. So energy would have increased in that case, because half into Kc V square, right?
Yes, sir.
You understand there are two different cases, no? There is one case where it was an isolated capacitor setting, right? Isolated.
Hmm.
When it's an isolated capacitor, charge is constant, right? Charge cannot be created or destroyed, right?
No, sir.
So initial energy would have been Q square by 2C.
Yes, sir.
Final energy would have been Q square by 2C dash. which is q square by 2 kc, right?
Oh, right, because yeah, the capacitance.
So energy stored in the electric field is now lesser, right?
Yes, sir.
Correct?
Yes, sir.
Because why did it happen? Because some of the energy went into arranging the dipole moments in the glass slab, no?
Okay, huh.
You understand? Who
Yes, sir.
Earlier there was vacuum, now you have put a glass slab, but somebody has made dipole moments, arranged the dipole moments in the glass slab, no? So some portion of that earlier energy in the field has been used up there.
Yes, sir.
You understand?
Understood, sir.
Therefore, it is looking less. It's not like energy has vanished, right? This is the energy that appears in the electric field, right? It looks to be less because some of the work was done to arrange dipole moments, right?
Yes, sir.
Now notice that in the other case, it is connected to a battery. So if you're connecting something to a battery, the thing that you're maintaining constant is there is V, right?
Potential difference, yeah.
You are maintaining V constant because battery can do some work and all, right? What it wants to maintain is V is constant, right?
Yes, sir.
So once that happens, half CV square is the appropriate formula that you should use for energy, right? Because V is constant, right? You should not use half Q square by 2C formula here. You know why, right? Because Q is not going to be same. Battery can supply charges to you, right?
Yes, understood.
So you should use energy formula half CV square and later it becomes half KCV square, right?
So in the isolated condition where there is no nothing to provide charge, we use q square by 2 kc and
Because obviously Q cannot
uh,
change, no?
yes, sir, it's
And
constant.
here when it is connected to a battery, you should use half CV square because V cannot change,
Oh, okay, okay, okay.
right?
Yes, sir, understood.
Because otherwise if you use other formulas, no, it will be quite confusing. Because Q will also change, no? So how will you decide both the things, right? You should use this formula, half kcv square, right? This now the energy looks to be more in the electric field, right? Correct,
Well, yes, yes.
right? This is because the battery is supplying some energy.
Yes, sir.
Okay, to keep maintaining the same field, see, to keep maintaining the same potential, battery must supply more energy or more charge and all, right? Because actually field was reduced by k, but battery is constantly maintaining same field, right? Somehow. So more
Yes, sir.
charge has been supplied basically, right?
Okay, sir.
You understand, no?
Yes, sir.
Okay. What other doubts are there in capacitors?
So this was the doubt, and just a minute. Sir, there is also one thing in. Okay, that's not done. Oh, sorry, sir. So there is one thing like
Hmm.
the loss of energy in sharing charges, sir. That topic I did not understand, sir.
Loss of energy in sharing charges.
Yes, sir.
So what type of question? Do you have any question?
No, sir. There is like some. There is this derivation which is given in NCRT, sir.
So
Like
tell me the statement of the question.
okay,
As in,
sir.
like, what happens? What is the setting? Two what is happening?
Yes, sir. So basically, when two charged capacitors are connected to each other,
Hmm. Okay, fine.
yeah, they share charges till they acquire a common potential.
So suppose Q and minus Q, Q1 and minus Q1, and this is C1, right?
Yes,
And
sir.
then there is Q2 and minus Q2, and this is C2, right? These two charged capacitors are going to be connected to each other, right?
Yes, sir.
Now you can connect it like this, correct?
Okay.
Now if you connect it with a wire, what happens is potential here in the wire is same and here it is same, right?
Okay.
Potential in this connected portion has to be same, no?
Yes, sir.
It cannot be that one portion of that wire is a different potential and another portion of the wire is a different potential, no?
Right, sir.
So if that is the case, then potential across this is V1 minus V2 and across this is also V1 minus V2, right?
Yes, sir.
So some charge might flow, okay? Some charge might flow from here to here, right? Correct?
Yes, sir.
So let's say Q1 minus Q and it became Q2 plus Q, right? Some charge flowed from here to here, okay?
Okay.
Correct?
Yes, sir.
So what we will have is that finally this is the final charges, Q1 minus Q, and because some charge went this side, then it will also become minus Q1 plus Q and minus Q2 minus Q, right? Right?
Yes, sir.
In the final situation, these are the charges, Q2 plus Q and Q1 minus Q,
Minus
right?
Q. Hmm.
Now you can say that potential across this capacitor is Q1 minus Q by C1 should be same as potential across this capacitor because that is V1 minus V2, right? Should be same as Q2 plus Q by C2, right?
Yes, sir.
Correct.
Yes, sir.
This is saying that potential across the capacitors are same because you have connected it like this, right? So then you get Q1 by C1 minus Q2 by C2 is equal to Q by 1 by C1 plus 1 by C2, right? So you get Q1 C2 minus Q2 C1 by C1 C2 is equal to Q C1 plus C2 by C1 C2, right?
Yes, sir.
So the amount of charge that flows is equal to Q1 C2 minus Q2 C1 by C1 plus C2, right?
Okay. Yes, sir.
This is the amount of charge that flows. So final charges now you can find out. Q1 minus Q is equal to Q1 minus Q1 C1 plus Q1 C2 minus Q1 C2 plus Q2 C1
Hmm.
by C1 plus C2. So Q1 C2, Q1 C2 cancels. It becomes Q1 plus Q2 into C1. So Q1 plus Q2 into C1 by C1 plus C2, right?
Yes, sir.
Correct.
Yes, sir.
This is the charge on the Q1 final, right? Basically what has happened is total charge Q1 plus Q2 was there, no? See, on
Huh.
the whole system that has been divided in the proportionality of C1 by C1 plus C2. So C1 fraction of it went into this one and C2 by C1 plus C2 will be here, right? Makes
Yes, sir.
sense. Q2 final will be the addition of Q2 plus small q and it will come out to be Q1 plus Q2 into C2 by C1 plus C2.
Right.
Now you can say initial energy was Q1 square by 2C1 here, Q1 square by 2C1 here, and plus Q2 square by 2C2 here, right?
Yes, sir.
And final energy will be different now, different it is, right? You can think of this as a parallel capacitor of charges Q1 plus Q2 and one capacitance, right? Which is the equivalent capacitance C1 C2 by C1 plus C2, right?
Right, sir.
Or you could also do it in part-wise manner like this, but that will be long unnecessarily. Like you can do Q1 plus Q2 square by this square by 2C1 plus this square by 2C2, right? Correct.
Yes, sir.
Find the final energy and initial energy. The change in energy is the loss in energy. Correct.
Yes, sir.
If final energy is looking like lesser than the initial energy, that means some energy has disappeared, right?
Yes, sir.
So, uh, you should actually do an HCV questions of capacitors. Okay, there are many questions like this in the exercise. If you look at question number 35, 40 onwards, right?
Huh.
35, 40 onwards till 60. There will be many questions like this. If you solve all of them, sorry, if you solve all of them, then you'll be well prepared for whatever exam. So make sure that you are attempting that, okay?
Yes, just a minute. 30.
30 onwards, basically. Sorry. Okay. So, with if there are no more doubts, then we'll stop here for today. Okay. Are there any more doubts?
No, sir.
Okay. So
Should
get
I also should I also do the frictions? The frictions I'm gonna ask you doubts in the next class, right?
so basically come with doubts from friction, capacitors, Gauss's law.
Yes,
But
sir.
we'll mostly focus on circular motion and we'll try to do circular motion work for energy in Sunday's class.
Okay,
Okay.
sir. Yes, sir.
We'll solve doubts in the beginning, but after that we'll focus on circular motion and that portion. Okay.
Okay, sir.
Okay. Work on the capacitor and Gauss's law though. You want to finish this off and move on. Okay.
Okay, sir.
Okay. Bye.
Thank you, sir.
Hmm.
Take care.
Okay.